Good morning, friends, and I welcome you to a webinar on predicting and avoiding plastic part manufacturing defects with SolidWorks plastics. So let me introduce you with the host of today. I am Ankur Sharma. I manage the simulation business for Dassault Systems SolidWorks. I'm joined with my colleague Gautam Srinivas and Pradeep Niduram, who are the respective subject matter expert on plastic part designing and injection molding process. We will be your host for the next hour or so, and we will try all our efforts to make the session extremely interactive and interesting for you. Before we get into the session content itself, let's have a quick poll questions to understand our audience and understand each one of you so that we are on the same page. So the poll question one is, what is your role in the injection molded plastic part uh, designing in your company? So the poll question is on your screen. Are you only designing plastic parts? Are you designing injection molds as well? Or you are designing both plastic part as well as injection mold, or you don't have anything to do with plastics in your company? The poll will last for 1 minute, 40 more seconds to go. What is your role in the injection molded plastic parts in your company? Do you design plastic parts? Do you design injection molds? You do both, or you don't do anything to do with plastics in your company? Thanks for your answer. Now let's get ahead with the sessions. So why are we having this session today is because plastics are everywhere. In industries like transportation and mobility, almost 50% of the parts are made of plastics nowadays. Any component which you touch and feel and or has a strength or a thermal maintenance requirement are also being made in plastics in times to come. When we look at high-tech industry, it's plastics everywhere. If we look at consumer goods like washing machines, air conditioners, mixer, grinders, all are made of plastics. When we look at consumer packaged goods, everything which you touch, hold, or use, may it be a toothpaste tube, may it be a hand dryer, may it be a toothbrush, may it be anything which is around you, is made up of plastics. And when we look at life sciences, everything in the life cycle and sciences industry is having a very significant plastic role. So that signifies how important this man-made polymer has become important for us and playing a major role in our day-to-day life because of its strength, manufacturability, as well as durability in our day-to-day usage. So while plastic parts are everywhere around us, they are also very challenging to manufacture because they are highly prone to manufacturing defects, which happen almost frequently when we try to design and manufacture them. Very simple aesthetic effects like air traps with burn marks, a part not filling properly resulting in short shots, an undesirable sink mark at a wrong location, or an unwanted weld line which should have been avoided. So these are very common, simple aesthetic problems which arise out of an plastic part which was designed perfectly but could not be manufactured because of a lot of constraints and limitations. And this requires a lot of back and forth movement between your tool maker and the product designer to arrive at a design which is acceptable. Let's see what are the typical challenges you as a designer face, since most of you told that you are in the plastic part designing. So what are a designer of a plastic part uh, faces as a day-to-day challenge is being able to predict manufacturability of designed parts while designing. Currently, you may be using any of the popular 3D modeling softwares like SolidWorks, CATIA, or anything else. But then at the same time, while you are designing a great product, there is very little insights about will it be injection molded properly? Will it not have the defects what we saw on the previous slides? So how do we generally take our decisions? We do most of the designs when, because we don't have a feedback about the manufacturability in the injection molding process, most of the designs we do, almost every design we do, is taken, a decision is taken based on our gut feel that I think it should be manufacturable. I pray there should not be a weld line. I wish there is not a sink mark. I wish it does not happen because I'm designing it and it seems right to me. And then I have designed it in the past so many times, but so that I should not get this problem now. But when decisions are taken in that manner, there are significant consequences. Um, Most of the time, basis our experience and understanding of dealing with the industry people, is when you do a plastic part design and assess its manufacturability basis your gut feel or experience, the serious consequences are the mold maker, when the part goes for the mold making, identifies manufacturability issues and comes back to you for a design change request. And that is where you have to start doing the design again, and you make a design change, probably add a feature, remove a feature, change a geometry, do anything. But then you still, since you do not have a feedback about the manufacturability again, it doesn't guarantees of solving the problem. And then the part goes back to the mold maker. The mold maker again finds another defect and comes back. And this cycle repeats so many number of times that the company starts losing profitability, product timelines, as well as the cost to make that product available in the market at the right time and in the right scenario. So with this, what are the mechanisms to address these kind of challenges? Before we go into details of that, let's understand each other slightly more better. Is how often do you get a plastic part design change request from the mold maker due to issues like sink marks, short shots, undesired weld lines, or air traps? So we would request your feedback here, which would help us assess your challenges in better details. And the question is, how often do you get a plastic part design change request from the mold maker due to issues like sink marks, short shots, undesired weld lines, air traps, etc.? Do you get it on all your designs? Do you get it on few of your designs? Or you do not get any such request from your mold maker? We have 20 more seconds into the poll. Thanks. We can end the poll. And now we have a follow-up question on this. To set the table and context right, is since almost every one of you said that you get this request at least some of the time, now how do you deal with this request? When you get such requests, how many rounds of design and mold rework are typically required before your mold produces acceptable quality parts? So let's have a quiz on that. We are trying to assess how severe or how intense the problem is for you. If you get such request, how many rounds of design and mold reworks are typically required before your mold produces acceptable quality parts? Does it happen in one iteration? Does it require two iterations, or does it require three and more iterations? We have 30 more seconds to go. So this question is applicable for people who face this problem. So if you don't face a problem, this question is not applicable to you. Thank you for your answers, and we appreciate your active participations. Now let's proceed ahead with the session. Is This is a typical design to manufacturing process of a plastic part, and it starts with the part design, mold design, followed by mold manufacturing, part production, and product launch. So what you see on the blue side, the blue highlighted area are the area where a small design change can make a big impact at a lowest possible cost. Whereas what you see in the orange is the cost of change. As it is adequately evident from this graph is, if you are able to identify and correct error at an early stage, you could make a correction at a much lower cost with a higher impact. So let's see how does it happens going forward is, what is the solution to be able to make a part design change at an early stage of design process while you're still at the 3D modeling stage and have maximum impact in avoiding any kind of manufacturing defect. And that is possible if you have the capability, technology, and power available to predict and correct manufacturing defects of a plastic injection molded part in the early stages of part design. And that is a concept which is called left shifting of it design, where most left is the area where we are on the early stage. We correct as many problem at the early stage so that our later stages become smoother. With this, let's move on. And let's spend some time on understanding how this will happen. So let me take you through a small introduction video of the concept what we are going to talk about, and then we will take a deep dive into the real operating procedures and technologies which are working behind this.
You've designed a great new plastic product and you need to get it to market quickly. So you need to optimize the parts for injection molding, which means you need to be sure the part thickness is uniform and won't warp, that the mold fills properly, that there are no defects such as blemishes, air traps, and flashing. The mold needs to be perfect the very first time or you will quickly be overcome with sinking profits. There has to be a better way. Enter SOLIDWORKS Plastics. Using SOLIDWORKS Plastics is the most efficient and accurate way to validate your plastic designs before you start injection molding. In a matter of minutes, you can easily test your designs for proper fill, best injection location, and potential product defects such as weld lines, short shots, and sink marks, all within the SOLIDWORKS interface. SOLIDWORKS Plastics takes the complexity out of testing your designs to ensure you get the mold right the very first time. It does all of the complicated calculations for you, so you can focus on designing. SOLIDWORKS Plastics works directly within the SOLIDWORKS interface, so you can validate while you work. You'll create the best design the first time, every time. To learn more about SOLIDWORKS Plastics, contact your SOLIDWORKS reseller or visit our website at www.solidworks.com. SOLIDWORKS Plastics. Eliminate costly mold rework, improve part quality, reduce time to market.
Now, let me hand my session to my colleague Gautam Srinivas, who will take you through a very interactive, interesting demonstration of the technology, how things are being done here, how do people solve this problem, and how SolidWorks plastic injection molding simulation technologies can be a big benefit to your organizations. Thanks for your listening. Over to you, Gautam.
Thanks, Ankur. Good morning, all. So let me take you through how we can build a better plastic component, how to make sure our plastic part is manufacturable. So I took an example to elaborate more on that. So what the product I took to demonstrate today is the MyoPro. MyoPro is an robotic arm where it will be help the paralyzed person to have regain his hand activities and all. So in this product, we trying to focus on this battery pack. In this, we have a door, a closer. So we will validate. This is made up of PC plus ABC, a blend of PC and ABC. We will validate this, like how we can do a design and check whether it is moldable or not. Okay. So we had chosen this. This is the part. This is the door closer, which we're going to discuss today. Okay, so what the things we going to focus is, we have two objectives. One is on the design review phase, and the other is the validation phase. In design review phase, we need to design this plastic part with by adding some fasteners, because this are like an easy to fit product. We need a snap hook and various mounting zones and all. So, and also we need to check what the draft angle and what the thickness distribution over the plastic part. By that, we need to build a better moldable plastic design. And on the validation side, we will go through the two design phase. One is the initial design. I will build the initial design and check for its manufacturability. And I'll also look on to go with one more revision, like building the part much more lightweight, and because this is like it is going to mount in the hand, so it need to be lightweight to handle very easily. And finally, we will build a report and look upon how to build a document which is shareable with everyone. Okay, let's go one by one. So let me take through the Sodos window. Sodos 3D CAD. You are familiar with the 3D designing, which is a very user to design, very user interface software. So we have the entire assemble of this product. So I like to open the cloud closer, and let us review the design of this. So this is the closer we had to. You can see there are multiple rips are there, and gear mechanism is there. So here we have one more support where we'll be placing the spring for less force to close this door. Okay, so let us see what are the first phase of design review. So what I like to trick through is how easily we can design this part, like adding some fastness over this. So I will suppress this feature. So I'll go for the edit mode. Okay, so let us see how to add this fastener very easily. In Sodos, we have an inbuilt tool setup for plastic part designs. Let's say if you're going to design any fasteners, you can see we have an virtual mold box tool, and then snap hook, and the snap hooks with grooves. And if there is any thermalness happening, we need to plan for any vent layout. So for the venting also, we have a separate tool, which are like, you don't need to create a sketch and extrude, or like you don't need to go for 5-6 steps to build this features. So let me take through by so in the snap hook design. So it asks for a reference place where we need to place our snap hook. So I will place it over here with some reference on the height and the width of the snap hook. And also we have the complete control of the geometry. Let's say the thickness and the draft angle and the height, every parameter you can change here, and you can save it as your favorite. So I had created my snap hook. You can see within less than a minute we create the snap hook, and I need one more instant over here. So I like to mirror the snap hook, so by using a symmetry plane over here. Okay, and I had picked this feature. You can see within a 2 steps we created the snap hook. So like that, we have multiple fastener tools within the design tool setup. Like you can go for here, you can look on the fastener features. Okay, so I had designed my part, but before validating, I need to see whether this will be fit in my mold, whether it is easy to edit from the mold tool. For that, we need to check for it a draft angle. So here you have an inbuilt draft analysis tool. You can go directly draft analysis tool, and you can pick the parting surface or parting plane. So if you pick on the parting surface or parting plane, let's say it is on okay, let me pick the flat face over here or any straight face over here. So software will predict me. So what the draft angle, if I say mention any draft angle, if it says positive draft and negative draft, and which are the areas the draft is required, like the software will give you an guidance. Okay, so when I okay with the draft angle, and one more thing I need to check on the thickness distribution over this part, because if I added more thickness in any of the regions, then it will result in some of the manufacturing defects like snap sort or something. So what we can do, we can go with thickness analysis tool, and we can calculate for that. So here software will give you a virtual plot about what are the regions has higher thickness and which the regions are more thin. So here you can see the graphically, so the very thin regions are in the red zones and the thick regions are in the blue zones. So and one more thing, if you drag your mouse pointer in the simultaneous, it will probe the thickness regions and it will give you the result. So you have a better view about the thickness distribution on overall over a component. Okay, so what we did, we had reviewed our design. So we had checked for its draft angle and the thickness distribution. Okay, so now I okay with my design. So this is my initial design. Now I need to look upon the manufacturability of this plastic component. So for that, you no need to export this component as a neutral file, as IGS or step file to any other for validation tool. Here comes the Sawdust Plastics, which is add-on to your Sawdust design platform. Okay, so in Sawdust Plastics, you can directly, you don't need to do any import or export. What are the 3D geometry you have with all the feature details, it will export to the validation tool. So here, what you need to convey, like the what are known parameters you have. Let's say what the material it is made up of, and where I need to get injected. Like first we will go with the material. So here I have set my injection unit. I need to set the parameter for the injection unit. So let me open and see what material is fit enough. So for that, you no need to manually feed the metal data for the software. We have an inbuilt metal library which is populated around 4,000 variants of material, with 4,000 grades of material, which is already pre-feeded in the material library with all the supplier name and the grade wise segregations. So for every material, you can see the polymer metal parameters. Let's say what's a melt temperature, what's a mold temperature, and the glass station temperature. Every data is pre-feeded. So this is material, but you are worried like what material is I need to choose. So let's say my need is the glass station temperature need to be in 120 or 130 degrees Celsius. So can software suggest what material grades are available for that? Yeah, it's there. You can go simply go for the search option, and in the option you can feed what the parameter you know or you like to search. By that, software will populate and show you these are the materials with the property which you required. And one more question may come. I have my custom own material, how to feed into the software. That also can be possible by using user defined database. Okay. So here I had chosen PC plus ABC blend, which are FR3010HF, which comes from the supplier of now Covestor. So why I choose this material? This is the best suited material for an electronic appliances, like it is a flame resistance, and this is like a consumer product. So it may have a hit over the product or a drop from a certain height. It need to withstand that shocks and the load. So this metal will be more stiff enough to handle those kind of load. So I picked this material for this component. Okay. So the next thing is we need to set the injection conditions, like the machine conditions. For that, what we can do, we here we comes the two approaches. One is like I have the design. Can you suggest me what are the setups I need to do in my injection unit? That is one objective. Other thing is I know my injection unit setup for this machine setup, like the melt temperature, mold temperature, and the injection pressure limit, and the time of the filling. For that, I need to know whether this part is fillable or not. These two cases can be validated with the sawdust plastics. Let's say if it from the automated approach, software will guide you through what are the machine setups you need to provide to have a better injectability. Or else, if you have your own data, you can go with the user defined, and you can feed your own machine setup condition, and you can check for it as fillable conditions. Okay, so both things you can do. Here I go with the automated approach. Okay, then the next question comes where I need to set my gate. So for gate selections, here also we have the two approaches. Software can guide you with auto predicting the gate location. So it will check for the geometry profile and it will suggest which location is best suit have for the uniform, like a uniform reachability of the molten polymer. So or else you can choose the phase, we can choose the vertex where the gate need to be, and you can define the size. While defining the gate location itself, you can able to predict how the fill pattern is going to look like. So here it will give a prediction of this. Okay, so once you are okay with the gate location, now we can go with the next setup, like the like of the fill condition setup. So how much tonnage is required to clamp my mold? So those tonnage you can see, and also you can provide the ambient temperature, ambient room temperature conditions. Okay, once you're done with the setup, now we need to turn this 3D model into one mathematical model. Like the parameters is feeded, it need to be calculated by using the solver. For that, we need to build this as a mathematical model called as mesh like FE approach. So for that, we have a multiple element type hexahedral, tetrahedral, and also we have a huge control over the mesh arrangements. By that, you can build a better quality mathematical model, and also we have multiple plots to validate whether this FEA model is good, or like an aspect ratio testing and various other quality tests we can be conducted. So once you're done with all the setup, you can run the study. By solving the study, you will get the results, like various forms of results as output. The first and primary result which we'll get is like how much time will take to fill this cavity. So here you can see like the fill time, the maximum fill time is required is around 1.07 seconds. So it is not only says what the seconds, how much time is required to fill this cavity. We can also virtually see how the molten polymer is flows inside my cavity. So you can see how beautifully it is animated, and at any time you can pause and you can see the how the growth ratio is. Okay, and let's say here it is how it is get transferred, and also let me pause over this region. So you can see there are some flow frences happen over this region. This is the through hole region where it is going to get mount. So there is some chances to build the weld lines, or the appearance of weld lines over this regions. Let us see whether we have any weld lines over this region. So I turn on the weld line option. You can see there are some weld lines built over this region. Okay, this is the critical load acting the region where the gearing system and the locking mechanism will be taken part here. Okay, and also pretty other weld lines are happens over this regions, but we need to know whether this weld line will affect my product quality or structural integrity. So for that, we need to look upon the flow front temperature. So molten polymer, the flow front temperature we need to look like here we have the gate. So the critical load acting region, here you can see the temperature is much more lesser. You can see the green zones, which the maximum flow front temperature 262, where this region you can see it is around 232 or less than 235. So if there is a less front flow temperature, then the structural integrity will affect. So we need to bring this gate as much near to the weld line locations. So by that it has a higher flow front temperature to build a better quality product. Okay, this so we have one more concern, and also you can look upon where the venting we need to plan by turning on the air trap option. So you can see where are the air traps is going to occur, so we can plan our venting system on that. Okay, and we have much more research. Let me deep dive onto the shrink mark. So here the shrink mark, you can see there are some imprints of the ribs. So where you can see the rib profiles are imprinted over the front face of the our door closer. So this will definitely affect our aesthetic of the product. And also you can see where the gate we had placed there, also the appearance aesthetic will be affected. Okay, this has a serious concern on that. But you can see this product is easy to fill, it won't sort. So, and what the pressure is required to fill this cavity, it is around 12.82, which is very minimal pressure for this cavity. So I had validated my first level of design. So let us review this design. Like we can see like it takes around 1.07 seconds with the 12.82 injection pressure, and the well lines are occurs over the critical load acting zones. So and also we could observe this well lines are far from our injection location. So this is a serious concern. It will affect the structural integrity. Okay, let us do the second design change. So in this second design change and the second iteration, what I like to do is I like to reduce the thickness of the front wall conditions to make this product much more lighter. Okay, and also one more suggestion what I have is I like to know when I shift this injection location from the middle to the bottom level. Now so to like if it is in a hidden area where the gate is get located, then it is where it won't affect the aesthetic. So the gate impression, it won't be affect the aesthetic. So I move my gate location from this middle to the bottom level, and also I reduce the part thickness by 0.5 mm. Around 0.5 mm I had reduced the wall thickness. Okay, let us see how this affects my results. So with this edited design and change in the gate location, we could observe the cavity will fill with the time frame of around 0.74 seconds, and the pressure needed is around 37 seconds. Why this has happened? Like the volume of the part is reduced, so the filling time is reduced, but also due to the thickness change, whether this is developed from the thick part to the thin part, the pressure shoot up a little bit high, but it is not a huge like it is not a huge. It is easy to fill. So when you look upon the easy to fill plot, you can see everything is turns in the green. Okay. So and the one more concern is the red lines. We have an issue like it has occurred on the critical load zones, but we will compare this with the flow front temperature. So flow front temperature, now we can see this is in the hot zone. So this entire region is turned into an orange and red, which is around 264 degrees Celsius. So this won't affect the structural integrity. Okay. So we could see there is a betterment in the second revision of the design. Okay, so in the second revision, we had changed the thickness of the prod and the gate location we get changed, and we can observe it took around 0.74 seconds with 74.4 megapascal of pressure to inject this part. And the mode front temperature is now closer to the well line, critical well line regions, which helps to improve the well line structural integrity. Okay, so and also we moved our gate from the center to the bottom level. By that, the gate impedance is produced, like the tackle field will defect will be reduced, or it is hidden from the exposed regions. Okay, so and also we need to build a better report, or we need to build a report which is shareable with others. For report generation, we have an automated tool which will help you by building the report in two formats. One is on the Word file and the other is the PPT format. It may show the report which we generated. This is the Word format file which has a product image with the tabulated content, and also all the details like what the material we used and the material property and the mesh condition like mathematical properties, and also it's populated with the results, all the plots which you see like the filled results and the pressure condition, the sigma profiles, flow front temperature, every plots will be get built. And also it comes up with the data charts like when the pressure is shoot up, at what time frame it is shoot up, and how much volume is filled at what time frame. Each and every detail is mentioned in this report. Okay, this is like in the documented manner. But one more concern I have, like I need to share this result with my manager or any people who like to review in a 3D way, like they need to zoom in and rotate, and they interested to share any comment of this product. In this phase, we have one more capability, like we can share this results as an e-drawing file. So the 3D data, like 3D results plots, you are sharing with your team. So by exporting the results as a e-drawing file, you can see when I open this e-drawing app, which is free to access either in a Windows platform or in an Apple platform, or whether in a computer or in a mobile device, anywhere they can open and see these results. They can rotate, they can zoom in, they can able to section the view, and also they can share their comments, whether it is approved or there is any comment they like to add, they can add over this part and then share you back the same content with you, so you can able to communicate with each other very easily, which is lightweighted result export tools. Okay, so you can see how we had validated and communicated the results with each other. But for every injection molding, there are some building blocks. Like first, we need to look upon what solver technology we are using, because solver technology or the equations which is built to predict the how plastic molten plastic part is mold inside our cavity. The exact prediction, the calculation need to be done. For that, Sawdust Plastics has a well-known or a robustic solver technology, which is tested with various virtual testing is virtual and real-world test comparisons is done, and it is proven technology we have. And the meshing technology, which is like it converting the 3D model and the data which is provided into a mathematical data, which all the elements, nodes, and the arrangement, the exact volume capturing need to be done. For that, we have a huge mesh element database and the controlling, which will be do well body fitted mesh, and it can be able to validate mathematically very robustic. That also compared with the real world test, and all the comparisons is done. And what about the material data? Because material data are feeded by us to the software. So this material data need to be best suited. So when we talk about the material data, how reliable it is, because when you look upon if you say the material type, it is as a nylon is not a single material. Even nylon has its multiple grades. We need to look upon the what grade we are using, whether it is 10% glass fiber or 20% glass fiber or the 30% glass fiber. This property will be changed. It affects the flow, molten flow directions or the parameters. So the grades is very important. And these material grades and these materials are calibrated by the metal suppliers. So we Dassault System had collaborated with the most world leading material manufacturers, as you see in the slide, like the SABIC, Conserve, or the Polyplast. These are the named list. We have much more material supply, world leading suppliers who knows the material very well. They had done the curve fitting, all the data they had done, and sat there. We got the material library from them and added to the sawdust plastics. So why it is? It is all like updated, like what are the current material property, what are the blend they have, every data we had fed into the sawdust plastic material library, which is populated around 4,000 variants of metal grades. And also we working with them continuously. By that, in upcoming release, we add 281 new materials with the 7 different suppliers in 2024 release of sawdust plastics. Okay, so and to we go one more step forward, like we doing material data as a service, as a customer. If you have any grade specific which are not mentioned in the library which we have, we can send us the metal grade which you like to which you are working on. So we will work with the supplier and the material manufacturer, and we will get the data from the material manufacturer, and we will review the material. We do the data fitting and data correction we will do, and we will give you an analytical, like a virtual test capability of material data, which is easily fed to the material library, and you can validate the results. This we will do this as a free of surface, as a valuable customer. So this Dassault system will help you to find your material grade, which is virtually testable. Okay, and also we had done various virtual testing. So this is one of the test data which is done by Sabic, which who was a world leading material supplier, material manufacturer. They did softest plastics result, the real world the lab test results. So in the left hand side you can see the results which we got from the sodas plastics, and the right hand side is the photography of the lab test results. Okay, so you can compare like for each condition we had stopped the machine and we had taken the short condition. So you can see like at the 10 percentage of fill, how the fill pattern is looks like when compared to the software result with the lab test results. So to go more, now the polymer has reached around 50 percentage of the time, and you can see when it's reached around on the through holes or the pin core pin areas, how the profile of the polymer it is looks like. So you can see the exact match between the both the lab test results of the software results. So you can see like materials plays a major role. Like it is not like taking a common material and testing a data. It need to be grade specific. So grade specific material is much more needed. Like if there is change in any of, if you added some colorant to the polymer, definitely it will affect the flow behavior of the polymer. So those curve fitting need to be done, and by that only you will get an accurate results. So we Deso system had tie up with the world leading material supplier, which has more reliable materials in the library, which helps you to validate your product in a more accurate manner. So what as a designer we can test? So we can able to find which is the better gate location to have a uniformity of the flow, and we can have an idea about whether the product which we design, either it is a very thin or stringent product, whether it is sort with the parameters are feeded, or where it will result in any of the flow front or raised steps or well lines, whether it is affect the structural integrity, we can able to get an answer. And if the polymers are using is a fiber reinforced, so what the fiber orientation is made up of, because we can't judge how the fiber will be oriented in the cavity of the product, because the orientation very important to see the load acting zone and how the load is transferred to the entire cavity level from the fitting zone to the load acting zone. So fiber orientation very important. That is exactly it will predict accurately in the sawdust plastics. And the well lines, it will be predicted. We can able to find a detailed way where the well line is there, and we can change the gate locations to transfer the well lines from the critical load dieting zones to the non-load regions. And sigma profiles we can plan based on like the distribution, thickness distribution, how we can plan everything. As a plastic part designer, we can able to build a build our plastic part in a more confident way. By that, what the area is like, you don't need to go with multiple iterations. You will have a better idea how my plastic part is manufacturable. For within a first iteration you can give a better results. So you can see in a half an hour of time frame, we had done two design iterations, and we had tested the data, and it's easy to set up, and we had to get a better results which are easy to observe and know more about our plastic part. So now I hand over the section to Ankur to summarize.
Thank you, Gautam. It was really engaging and informative. The information you could pack in 30 minutes of time. And that I'm sure that would have given an idea to all of our attendees how simple, powerful, and capable this tool is when it is, and the benefits what a plastic part designer who is using SolidWorks or any other CAD software can benefit from this technology by being able to see the manufacturability of the plastic parts while they are still designing. So what are the salient benefits what the plastic injection molding simulation from SolidWorks bring to you? The first and the foremost benefit which is evidently available is you will be able to predict and avoid manufacturing defects early. So most of the aesthetic defects like we saw, sink marks, short shots, unfilled parts, as well as weld lines and others, those issues would be known while you are designing. So you will not have an issue about going them later and then wasting time, cost, and efforts in correcting them. It would also help you reduce late stage design change requests. That mold maker will be very happy to get the kind of designs what you're making, because they would not be aesthetic issues coming up in the first pass most of the time. So there would be the number of cycles for finalizing a design for moldability would be reduced significantly. At the same time, it will help you reduce design rework because you're correcting problems on the design table itself. So it would be a big time and cost saving. While this is happening, it would also reduce costly prototypes, because if you based on the poll questions what you answered, many of us are doing minimum of 2 to 3 prototypes before a mold is finalized. And you all know the cost of the molding prototyping process. And if you're able to reduce even that by 50%, you can imagine the cost, which will be significant. And at the same time, plastics are considered to be a material which is not so great for our environment if it ends in the landfill. So it would also help you reduce any of the wastage of the plastic part which goes in prototyping, which generally ends up in a wastage. So that could be completely saved. Also, it would also save a lot of money in terms of the cost of the plastic part, which is being wasted in the process. And over and above all, while you get all the benefits listed here, it would help you gain the confidence that what you are designing is manufacturable. And that's like a magical tool available to the designers to be able to design a plastic part with confidence that it will be manufactured the way it has been designed. With this, we come towards the final poll for the day. Is this is what you have seen during the past 45 minutes. Do you think that if you have the ability to validate the manufacturability of my plastic parts early in the design phase is going to help you? This question is to assess your interest and establish contact with you to help you know more about these tools. Do you think what you saw today was a great idea and you want to be contacted for further discussions? Do you think it was a good idea and you would like to know more through emails, or you don't think you need to be contacted so that we would not bother you? Great, thank you. Thanks for your participation. And with this, we come towards the end of the session. I thank each one of you for your attendance, time, patience, and contribution to this session, which is a huge encouragement to be knowing that we could be of help to a large audience of people. And we will be contacting you basis the interest what you have expressed. And we look forward towards welcoming you to this exciting world of injection molding for designers, so that they are able to make design with confidence and make plastic parts with no aesthetic and visual defects. Thank you once again. And we are signing off with your permission, and we will hope to see you soon again. Have a great day. Bye bye.